and they can store energy a little bit. But it takes photosynthesis to significantly, but that's not enough energy. It would follow this line right here if that's all we could do. Invention of photosynthesis actually allowed the net energy capture of the Earth to go up. It allowed it to actually store energy in the form of oxygen, and that energy came from the sun on a billion-year time scale. So that's the question of the planet actually being transformed. When we eat plants, we benefit from them. When we breathe oxygen, we also benefit from this energy capture. So I just want you to look at it as a big picture delta G kind of thing. Okay? The free energy in the initial state, if you have carbon monoxide and H2O, let's talk about how early life got energy. Then the initial state is that the early life lives and it makes structures, and it actually photosynthesizes. It forms more complex molecules, so it forms bonds between these simple molecules, and it makes oxygen. This takes energy. It takes sunlight to do this photosynthesis step. Once it's done, however, these structures sit around until sometime later when you take them and you combine them again. When you're burning something, you're doing reverse photosynthesis because you're taking the oxygen and the sugar, when you're burning a plant, let's say, oxygen and the plant, and you're putting them back together. You're making CO, CO2, H2O again, and heat is given out. Energy is put in from the sun, heat is given out from the combustion. Okay, so just have this image that the sun, and remember that we have the whole thing about high energy light comes in, low entropy light comes in, dispersed energy, high entropy light or heat comes out. Remember that heat is actually a form of radiation. IR is a form of light. We just can't see it. So visible light in, UV light in, IR light out. And this whole thing allows this cycle to turn. And the more it turns, the more this gets transformed. So you can have life without sunlight, but it's going to be different. It's even differently colored. This is This is a big panel, and they have mud in it in the exploratorium. And they have these flaps that block out the sunlight. It's in a sunny room. You can see the reflections of the windows on it. And you pull open the flap, and you can see outside the flap you have these bright colors, green, red. These are different kinds of photosynthesis. These are somehow collecting visible light because they have the visible colors. Under the flap, where it's been blocked from sunlight, you don't have any of that. You don't have any photosynthesis going on. It's dull. They don't need to absorb visible light. And so what's interesting is that, before oxygen, you had things that were working on different kinds of photosynthesis, perhaps. You had things that were making oxygen at the very most and not making much of it. So in this methanogen sort of stage, chapter 6 sort of stage, a lot of life ended up being purple. Right here you have purple sulfur bacteria. It turns out these are purple because of the wavelengths. They're purple and red bacteria. And it turns out that that's all the energy you need. That collects the energy that you need to be able to do photosynthesis type light-driven reactions on sulfur and methane. You need more energy to do the reactions on water, and that's why you need actually green light is the wavelength that you need for that. Okay? So, and so this is the purple sulfur bacteria, not very colorful. After oxygen, life got more colorful because after oxygen, you're doing more and more photosynthesis to make more and more oxygen so you can use more and more oxygen. And the photosynthetic life is green and red, and you can see it's cyanobacteria, which even contains the idea of the cyan color in it. Okay. Okay, so this is one of the main charts from the whole book, that the oxygen in the atmosphere increase over time. It's not a straight line, right? And it's also a log scale. Notice that over here. But you have these spikes and oscillations, but then it jumps up. And if you have two major events, if you want to say what are the two major events, Oxygen jumped up first, made a lot of banded iron formations, and oxygen jumped up second, and the evidence for that is in a second wave of banded iron formations that shows up. So you have photosynthesis. The best we've been able to date for when photosynthesis was invented was around 3 billion years ago, right before the oxygen started to go up. Now, we're not entirely sure that we know it was a factor. Was photosynthesis the factor? Or was it possibly the hydrogen escape that enriched the oxygen? There could be another mechanism. If I had to bet, I would say it's the photosynthesis, though. Because look at this. This is circumstantial evidence, right? But it was invented, and then all of a sudden oxygen went up. That's not airtight evidence, but it's good evidence. And the other major graph to always remember from the book is this graph that's a big arrow, because the oxygen goes up over time. Oxygen affects everything else, and chapter 5 concept, oxygen increases the redox potential expressed in this way. So as you're going up in oxygen, the natural state of each element is going to change. And it's going to change for the ones with a lower E value before it will change for the ones with the higher E value. So if you see this, you would say, okay, my ammonia is going to be transformed to nitrogen first, then my sulfur is going to be transformed to sulfate, and then down here, after oxygen fills the atmosphere, my ammonia is going to be transformed into nitrate. It's easier to turn Fe from its +2 form to the +3, so you would predict that that would happen before copper turns from +1 to +2. And again, this is all big picture, small detail type stuff. You can probably compare things, but and you can make guesses. And on a planetary scale, there's evidence that this happened. Okay, but it depends on a few other factors other than redox potential. This is one of the factors ordering when it was used by life. I made it an arrow because R.J.P. Williams, sometimes, I don't understand why he does some of the things he does. He put it in the form of a wheel, and he split the metals from the non-metals. But if you look at this, these are also redox potentials. This is actually the data that I got my arrow from. But to me, this doesn't express the main idea, which is that you had an arrow, you have an early time when you had a certain redox potential, and you have a late time when you have another redox potential. This is all redox potentials. It's just a question of how you arrange them. Unfortunately, he's passed away, so I'll never get the chance to ask him, at least not for a long time, for why he did this. But I think that the arrow gets the same idea around. But you can see the same sequence. You can see that nitrate got changed into nitrate, and you got more oxygens. Okay, you got more oxygens on sulfur. You got sulfate instead of sulfide. And you got more oxygens on carbon. You got CO2 instead of CH4 or CO. Again, the whole balance of the planet changed to being toward oxygen stuck to stuff rather than oxygen stuck in the crust or stuck in water. Iron, too, became more rare, for instance, and that's shown in the same kind of thing over here. So that's great. That's all an organic chemist, an inorganic chemist, actually talking about what he thought happened. Where's the data for it? Well, he wasn't working from genes. Around 2000, of course, we got to sequencing technology where we could sequence tons of genomes. And there's a group that actually looked at the genes and said, when did genes show metals being used? And the interesting thing is, for all my caveats about, okay, you can't tell order from this or things like that, you can actually tell enough order that R.J.P. Williams' predictions pretty much matches their results, okay? The other interesting thing is, by the way, Eric Alm went through my graduate school program. He actually went through my program like a year before me, and then he went on to do this. I hadn't known R.J.P. Williams, but it's interesting that the best confirmation of Williams' work comes from somebody that I actually knew. I haven't talked to him since, and should say hi sometime or look him up. But the thing about him is they did biochemical calculations. They looked at the genes and they tried to say, you know, when do genes use certain elements? And so you have this whole list of metals and nonmetals. The biggest thing is that you have oxygen on the top. And the main thing about that, oxygen increases over time. So blue means it's not used very much. Red means it's used a lot. And they sort of calibrated everything else to oxygen because you see oxygen not used very much, used a lot. So blue going to white means it's going up. Red going to white means it's going down. And so this goes with what Williams said. If you look down here, sulfate, blue, sulfide, red. So the H form goes down, the O form goes up, and you can see that the other sulfates actually go with that as well. Copper goes up. Molybdenum goes up. That was actually on the chart as well. Manganese goes down. This is actually, you predict, because its most useful form is actually going down over time. Cobalt goes, cobalt actually goes, it has this little blue blip at the front, but it's mostly red. You can see for most of its history it's red, and it predicts it would be red. So I'll take that as a green. Now, so I think that most of these are showing up in patterns that go along with what we saw. Zinc is kind of like, well, I don't think there's just much data there. It's not showing that zinc's going up or down. Nickel actually goes in the opposite way. Nickel goes blue, whereas we said it goes red. It should be red. Now, the one thing about that is, if you remember from the book, we also have the nickel famine. And the nickel famine would not be reflected in its redox potential. It would be reflected in its melting point. And so this might even be said to fit, but it doesn't fit the redox potential itself. And, you know, the iron in itself is also not reflected, but iron also is so useful that we've scraped and scrambled to be able to get it from the environment, and that could be a confounding factor as well. So complex system, lots of stuff going on, but in general, there's a lot more things that you're like, oh, that fits, than things that you have to explain away, okay? So that's, and if you look down here, you see the same trend for sulfur that you do for nitrogen and carbon. You use more oxygen over time, and it's confirmed by this independent analysis for all sorts of things. They made it one of the main points of their paper, actually, that oxygen-using genes were born, and they actually did this chart of when oxygen-binding genes, when they were born, when they first appeared on the screen, in the genes, okay? And they look at this. It's exactly around 3.0 billion years ago, which is right before the first oxidation event, right here. So you have the genes being born. You definitely can't say that the genes were born as an effect of the first oxidation event. This is entirely consistent with them being a cause of the first oxidation event.
How do we measure the first oxidation event?
Well, the biggest thing was the banded iron formations and geologists dating those. And the thing about those is they're found literally all around the world. And so it was a global event, so that's why global, and they include oxygen, so oxidation. And there's a lot of other evidence that's been put together as well to result in that. But the banded iron formations, actually I should have taken it. I have a mini museum with a little chunk of a banded iron formation in it. So I can show you that in lab tomorrow maybe or something like that.
You brought it to the capstone.
Oh, right. Okay, so I have put that to use. It costs enough money.
In lab, did you get it this year?
Yes.
I remember when we were in lab and we were looking at it online.
Right, and I was like, it's $300. So by the way, please don't steal it. But but I took it over to Canada and I showed them in my talk this weekend. You know, so. So it stands to reason. All this adds together to say, after oxygen, you have different metals. With different metals, different enzymes new enzymes can do new things. This is, again, R.J.P. Williams' prediction for what metals would do what reactions in which enzymes. But you can have all those categories. I mean, R.J.P. Williams was, he had a ton of information in his head. And I just want to show you that this is his way of getting his information out. And I think what's interesting is actually if you look at molybdenum, remember that's not just solubility. When you have the banded iron formations, that's solubility. It's becoming solid and sinking to the bottom of the ocean. Not everything changed its solubility. Sometimes it just changed its oxidation state. But it turns out that molybdenum changed from a +4 to a +6 oxidation state. And it became the only thing that could do a +6 oxidation state. But the +6 was not available before oxygen. So that's a case of a charge becoming more available. Same thing though. You're talking about electrons moving. You're talking about an E value. And molybdenum is actually used in two enzymes that actually react with oxygen-containing things. Your ethanol detoxifying enzyme and your sulfite detoxifying enzyme both use molybdenum to move oxygens around. So molybdenum